Hello, everyone. My name is Jennifer Storm Elves. I'm the LOCSEC of San Francisco Regional Mensa. I would like to introduce today's speaker. We have with us Ejner Fulsang. Ejner will discuss the general evolution that a society will have to make in order to become a true spacefaring society. The talk addresses the science and technology behind the series. It focuses on propulsion, space habitats, mission architecture, and genetic modifications necessary to become a space-adapted human. All concepts presented are plausible. Ejner graduated from West Point with a BS in engineering and flew choppers in Korea. After leaving the Army, Ejner spent 20 years working in engineering and marketing. He spent 10 years as a proposal manager at NASA Ames and SETI. 20 years ago, Ejner took up writing. He is best known for the hard SciFi Galactican Series. He is currently working on the 4th book of a planned 6. And I'm excited because we did have you at our RG this last time around, and as I was the co-chair here with Judy, I was only able to pop in and out for brief moments of time, so I did not get to see the bulk of your presentation. So this is terrific. I'm very much looking forward to hearing your talk today. So thank you very much. Without further ado, let's listen to our speaker, Ejner Fulsang.
Thank you, Jennifer. I'm really pleased to be here today. Let me start off with my email. If anybody wants a copy of this in PDF form, I'm happy to send it to you free of charge. And this way you can get the content of what I say. Plus, you can, at the bottom of most slides, I have a URL, which is all my source information. So you can dive into this topic, which is a favorite of mine, just as deeply as you wish. Okay, let's see, a bit about myself. As Jennifer mentioned, I spent 10 years at NASA as a tech writer, helping scientists write proposals for space missions. And today I'm hard at work on the Galactican Series, which showcases the technological and biological evolution that we need to become a true spacefaring society. Now, I define true spacefaring society as a society that routinely travels among the stars, at least the nearby stars. Galaxy, that's a bit much, but definitely among the nearby stars. So anyway, the first 3 of a planned 6 books have already been completed, and you can find them on the link below. They're on Amazon. These book covers, by the way, were all done by Douglas Schrock, who's an outstanding master space artist. These 3 books are still in progress. I'm madly at work on Enceladus right now, and I hope to have it completed by Christmas of 2023. And unmute.
I know we had a little, let me unmute yourself again.
I did. Okay, am I?
You're good now.
Okay, so every time I see that sign, I should unmute myself. Okay. Anyway, a comment about my writing style. I write in a subgenre known as hard sci-fi, the operative word being hard. What that means is that every element of science and technology has to be plausible. And for the more far out stuff, I have to prove its plausibility in the narrative of the story. And yes, this can make my books difficult to read, especially for the folks that are more used to Star Trek and Star Wars and Marvel Comics. So anyway, that said, why should we become a spacefaring society? Well, in 1950, Enrico Fermi asked a question: where are they? His now famous paradox referred to alien visitations, perhaps inspired by the Roswell incident of 1947. Now, regardless of what you think about Roswell, it was still a damn good question. With 400 billion stars in our galaxy, you'd think we'd be crawling with aliens. Later, in 1961, SETI astronomer Frank Drake derived his eponymous equation. Basically, what it seeks to calculate is the estimated number of technologically advanced civilizations in the Milky Way galaxy. And you can look this up on Wikipedia, and the beauty of it is that there are no correct answers. or rather no incorrect answers, and you can play with it and have all kinds of fun. Carl Sagan at the time, ever the optimist, suggested that n might be in the millions. So my question to Carl, posthumously, is, okay, where are they? Now, I offer two complementary hypotheses in response to the Fermi paradox. Pardon me while I take a small sip of that. Anyway, Brownlee and Ward's rare earth hypothesis was published in the year 2000. Essentially, they have capitalized on the fact that our knowledge of planetary science is vastly more sophisticated than it was in 1961. Truly, what we found out since then is that truly Earth-like planets are quite rare, as substantiated by the Kepler mission. And while intelligent civilizations may be rare, microbial worlds may be common. Any planet or moon with an internal heat source and a liquid ocean will suffice. N, the number of technologically advanced civilizations, may, however, be closer to 1 than a million. Brownlee and Ward's hypothesis implies that we never see alien civilizations because, frankly, there aren't any. Present company accepted. Okay, then the second hypothesis is one that I ran into just recently. It's Robin Hansen's Great Filter hypothesis from 1998. Robin Hansen is an economist by trade, but for some reason he's got into dibble-dabbling around in this area, and he's got a lot of interesting, albeit controversial ideas. What he suggests is that all civilizations must clear a succession of filters if they are to survive. So I have a list of about 5 here for our own society. Origin of life starts at the prokaryote level. Microbial life evolves into eukaryotes and complex multicellular life. That complex life becomes intelligent. Intelligent life becomes technologically advanced, and finally it ventures into space, roughly where we are on Earth today. But then's where it gets interesting. That we are still here today begs the question, might our great filter still be ahead of us? Humanity could author its own demise. Nuclear war, climate change, resource exhaustion, overpopulation. These are disasters that could occur somewhere in the centuries to millennia time frame. Or we could be wiped out from natural causes. Earth averages a mass extinction every 100 million years. Eventually, the sun will run out of fuel and become a white dwarf. That's inevitable, and we expect that to happen in the next 4 billion years or so. Now, though I point out that on a practical time scale, humanity authoring its own demise is on a scale of centuries to millennia. Natural disasters might be millennia to eons. Anything that I'm describing here could start happening in the next 10 minutes. Now, does that mean that you should run out and get in one last trip to Disneyland? Nah. But on the other hand, it does suggest that maybe finding an Earth B would be a good idea. Anyway, Hansen's hypothesis implies that we never see alien civilizations because they fail to become spacefaring societies, which is something perhaps we need to do. Okay, newsflash, Earth has a use-by date. If humanity is to survive, we got to get off this rock. It's not going to happen overnight. I see it requiring several centuries and requiring trillions of dollars. It will not be achievable by Earth's extant political and space infrastructure. Hence, the Galactican Series is set in the background of a dystopic Earth that is slowly succumbing to environmental, economic, and political collapse with widespread internecine warfare among the nations. Space Corp, the first book, takes place in the 2069 to 73 timeframe. It restores Leo with a giant space station after losing it to the Kessler syndrome. I'll talk more about that in a minute. Meanwhile, America undergoes a bloodless civil war and dissolves into 6 separate regions. Space Corp assumes control of the new nation of Sierra along the western seaboard. Cal exit, everybody. Cisluna, the second book, takes place in 2085. Essentially, after dominating Leo, Space Corp has migrated to Cisluna, the area around the moon, by the time of the story, and there are over a dozen space stations orbiting the Earth Moon Lagrange point number 1. Genesis 2 in 2102, Space Corp has discovered alien microbes on Mars. And within 10 years after that, there's a permanent space station orbiting Mars. Enceladus, the book I'm working on now, takes place 2155. Space Corps discovers alien life under the ice on Enceladus. Pluto, 2165, Space Corps discovers more life under the ice on Pluto. So basically it perpetuates the idea that any planet or moon with a liquid ocean and a heat source is a possible host for microbial life. The last book, Ross 128b, takes place in the 2200 to 2345 time frame, and that involves Space Corps sending a fleet of 4 ships to investigate a mysterious laser beacon emanating from the backside of Ross 128b. That planet or that star system is 11 light years away. Okay, instead of being an overnight process, I suggested it's going to be an evolutionary process. Initially, we focus on space propulsion and habitats designed for LEO and Cisluna with scientific excursions to Mars. Later, the focus expands to more advanced propulsion and a new species of genetically adapted humans called galacticans, who are engineered to be resistant to the hostile radiation of space and provided with life extension treatments that allow them to endure long transit times for trips to the outer solar system and beyond. Yes, that is plausible. Finally, in Book 6, Space Corps constructs a fleet of generation starships to begin humanity's interstellar diaspora. Each fleet is capable of replicating itself in both crew and equipment, sending the new fleet off to continue the diaspora. Now, I should point out that the Galactican series differs from other sci-fi books in that Galacticans do not colonize other planets and moons. Terraforming is verboten. Rather, they bring their habitats with them. They're kind of like turtles in that way. They replenish their stores as needed from alien asteroid belts, and their primary interest in alien planets and moons is to search for microbes from which they harvest alien DNA, their main business line. Okay, now that you have the general idea, let's take a deeper look into the science and technology behind the Galactican series. We'll start with books 1 and 2, Space Corps and Cisluna. Okay, the primary driver for Space Corps, the first book, is the Kessler syndrome. Now, basically, I like this graph because it shows how many satellites we have and approximately where they are. So we've got 3,790 satellites in low Earth orbit, which goes out to about 2,000 kilometers. It's bounded by the innermost layer of the Van Allen radiation belt. Then we have the medium Earth orbit, which goes from about 2,000 out to about 35,000 kilometers. And then there's the geosynchronous and geostationary orbits that are out at precisely 35,786 kilometers. And then there are the highly elliptical orbits, which vary as to what their apogee and perigee is. Okay, now here's the problem with that. In 1978, NASA scientist Donald J. Kessler proposed that the density of space junk in low Earth orbit is high enough that collisions between objects could cause a chain reaction in which each collision generates more space debris that increases the likelihood of further collisions. An estimated 130 million man-made fragments smaller than a millimeter are orbiting Earth right now. This one map here gives you an idea of what that junk density is looking like. Now, you should keep in mind that a 1 kilogram object impacting at 10 kilometers a second is capable of destroying 1,000 kilogram spacecraft. And in fact, in 2020, the ISS had to perform emergency maneuvers 3 times to avoid collisions with space debris. Over here on the left, I have an impact hole left in the Hubble Space Telescope back in 1997. Okay, now taking that, I then developed a timeline for the Space Corps book, which was published first in 2014. First, we start out with some actual events. These are things that did actually happen. In 1985, the Air Force decided they'd shoot down a research satellite with an anti-satellite missile. They were successful, and they produced an undisclosed quantity of debris. Then in 2006, not to be outdone by the Air Force, the Navy decided to shoot down a spy satellite with their own ASAT, again producing an undisclosed quantity of debris. This again was deliberate. Then the Chinese got into the act. They shot down a weather satellite in 2007 with their own ASAT. This time we have a pretty accurate estimate of some 3,000 pieces of space debris. And then finally in 2009, there was the accidental collision between the Iridium communications satellite and a Cosmos communication satellite, a Russian one. They produced a combined 1,788 pieces of space debris. Okay, based on that, I then began to speculate. And perhaps I'm a bit aggressive on my dates, but I started out in 2014. So anyway, I suggested that 10 years later in 2024, nuclear proliferation will now be common amongst second and third world nations. However, they recognize that their nuclear weapons arsenals are primarily political immunity devices. They have taken well the lessons of Manuel Noriega, Muammar Gaddafi, and Saddam Hussein, and Kim Jong-un. Hence, rogue nations that adapt their ICBMs into ASATs to shoot down derelict satellites in LEO in order to strut their technological stuff in the global arena. This hobby will catalyze Kessler's non-viability of LEO to a date well before that of the ChatGPT forecast. Excuse me.
Ejner, can you explain the ChatGPT forecast?
Sure. Basically, just for grins, ChatGPT being very popular these days, I asked it how soon would it be before LEO became non-viable due to the Kessler effect, and it came back and said 30 to 50 years. I thought, cool. And so I decided, okay, let me use that as kind of a baseline and then see how I did with my projection from back in 2014. In 2028, let's see, based on what this hobby of the second and third world nations, the average lifespan of a satellite is down to 3 months due to increasing density of space debris. Lloyd's of London has declared that it can no longer insure satellites and commercial operations in LEO cease. Now that is a big deal. Okay, that means no more navigation, no more communications, no more surveillance. Okay, continuing, in 2030, Space Corp initiates the construction of a space station called the SSS Wernher von Braun. It's a 1 kilometer spinning ring advertised as the first debris-proof instrument hosting space platform. It took them 8 years to get it built. 45 astronauts were killed and 427 wounded by debris strikes during its 8-year construction period. Okay, the von Braun is heavily armored to ward off small to medium-sized debris. Anything larger requires rapid avoidance maneuvering from her nuclear thrusters. For the inevitable impact damage that does occur, von Braun carries a human crew of some 737 engineers and craftsmen to assess damage, design and fashion repair parts, and program robots that then go into harm's way to install the fixes. In 2069, problems arise when the Iranian Space Agency attempts to shoot down a derelict Centaur rocket booster that's been in a graveyard orbit for decades. Basically what we do with these Centaur boosters is we use them for as long as we need them, and then we use their remaining fuel to scoot them up into a graveyard orbit where they're out of the way of other more productive satellites. It ends up putting them into a highly elliptical orbit, and when they come down into their closest distance to the Earth, then they become fair game for rogue nations like Iran who want to try to shoot one down. So Iran did manage to knock the Centaur out of orbit into a collision trajectory with the Von Braun. Although comparatively small at 2 tons, the combined speed of 40,000 kilometers per hour was enough to shear the habitat ring. This incident started the vendetta that arcs through the next 3 books in the series. You got to have a villain to have a good story, and I picked Iran. Anyway, in spite of this setback, Space Corps manages to install over 15 1-kilometer space stations into LEO. All of them are dedicated communications, surveillance, research, and navigation platforms. The heavily armored ring-shaped form factor of Von Braun solves 2 immediate problems of living in space: the high ambient radiation and zero-G. Okay, ionizing radiation is very damaging to DNA. Now, what do we mean by that? Essentially, it's radiation powerful enough to knock an electron out of its orbit, leaving behind a positively charged ion. Since electrons are essential to chemical bonding, sufficiently strong radiation in the form of UV, X-rays, or gamma rays can potentially disintegrate a molecule into its constituent elements. We get this kind of damage occurring on our bodies all the time, but DNA has a natural and inborn ability to repair itself. And as long as you don't get too many piling up at once, we can generally keep up with the damage. But if you get into a very high radiation environment, in space, there are quite a few of those, then you won't be able to keep up, and basically you will die a miserable death very soon. So basically, interstellar space is good for about 70 REMs a year. I should point out that an acute dose of 450 REMs is enough to kill a human. Interplanetary space is about 25 REMs a year, and the lunar surface is about 10, and low Earth orbit is a little bit less than that. The Van Allen belt has a whopping 1,500 REMs a year. And then, surprise, the Jovian moons out around Jupiter have some astronomical radiation levels because of their close proximity to Jupiter. Io, in particular, is a son of a gun. You would not want to be vacationing in Io anytime soon. As you can see, it's got 1,300,000 REMs per year. That will fry you fast and in a hurry. I remember watching a sci-fi movie one time where they had a mining operation going on in Io, and I was thinking, oh my God, how are they doing that? Now, the Van Allen belt is nothing to sneeze at either. It's one of the favorite arguments of the conspiracy crowd that says that the moon landing was faked. How could you get the astronauts to fly to the moon without being destroyed by the Van Allen belt? Well, the answer is it's shaped like a donut, and essentially what they did is they hopped over the upper edge of the Van Allen belt, and they went through it very quickly, and so they came through fairly unharmed. Nevertheless, the Van Allen belt does pose quite a problem for other types of space launches, which I'll get into later. Okay. There are other radiation sources in space that we need to think about. We have on Earth a Van Allen radiation belt. However, any planet with a magnetic field will also have one. Whether it's a very powerful one or not depends, but nevertheless, anytime we're looking at a distant planet and we spot an aurora on one of the poles, that's a sure sign it has a magnetic field and a Van Allen belt. Okay, coronal mass ejections from the sun. They send out clouds of radioactive matter. You get caught in the middle of one and you can fry pretty quickly. Cosmic rays, basically these are all the gamma rays and whatnot that emanate from the sun and penetrate from the rest of the galaxy into our own heliosphere. Space dust. This is one people don't generally think about, but when you're traveling at fractional light speeds outside the solar system, you discover that space is not a perfect vacuum. There is in fact approximately 1 hydrogen atom every cubic meter. And when you're traveling at very, very high speeds, they in effect produce their own form of radiation, which can be very damaging to your spacecraft. Then there's all the radioactive equipment, rockets, reactors, plutonium-238, you name it. And I've got a whole list of sources down here that are very informative as to what the true nature of all these radiations problems are like. Okay, the other problem that we have is the lack of gravity in space. Astronauts returning from only 6 months in the zero-G conditions of the ISS are unable to walk due to loss of bone density and muscle tone. They always show a group shot, and they always show them in wheelchairs. And this is in spite of exercising vigorously for 2 hours a day. Now, I don't exercise 2 hours a day, so I'm trying to imagine what it must be like on the ISS having to sweat through a full 2 hours a day, 7 days a week. A 4-year study of the long-term effects of microgravity on the bones of ISS crew members showed that on average they lose about 11% of their total hip bone mass over the course of the mission. And researchers say it could take much longer than a year to regain the lost strength. Bone loss during the course of a long transit to Mars, typically a Mars trip takes you about 6-8 months to get there. But to get there and back would result in an increase of bone fracture during the activities on the Martian surface. Mars is only 1/3 G. So if you're suffering that much bone loss that you could actually damage yourself while romping around on the Martian surface, this shows that we've got quite a serious problem. The ideal solution is a centrifugal force acting on a ring-shaped space station or habitat section of a spacecraft. This is what I'm showing here with the Baruki. Now, the Baruki is a kilometer in diameter, and it rotates at 1.34 RPM. This gives it an outer edge speed of about 70 meters per second, which sounds blindingly fast if you're standing there. But on the other hand, here on the surface of the Earth, we're typically traveling around 1,000 miles per hour, and we don't notice that. So anyway, the idea of having a ring-shaped habitat section that rotates is a very simple solution to the gravity problem, but one for which NASA and the rest of the space agencies has not put a lot of stock in. I should point out that the Baruki is named for William Baruki, who was the PI of the Kepler mission. When I was at Ames, Bill's office was right down the hall from mine. So one day I popped in and asked him if he'd mind if I named a space station after him. He was pretty tickled. The space shuttle that you see there is named for an engineer friend of mine at Ames named John Marmee. Okay, the next question is where to put your space station. Now, you could put them in Leo, and Leo requires delta V of 9.5 kilometers a second to get there. It's the best payload payoff for things like the Space Launch System, Falcon Heavy, and Elon Starship when he ever gets around to launching it. You have to consider, however, that any spacecraft that you want to launch into deep space are going to have to go through the Van Allen belt, and since they tend to have very low thrust to weight ratios, they end up having to spiral through the Van Allen belt, which is not a good thing. Okay, then there's GEO. It requires a delta V of 13.4 kilometers per second, and its payload payoff is cut to less than half compared to LEO. It is, however, at least a little bit past the Van Allen belt. My favorite is the Earth-Moon Lagrange point. Earth-Moon Lagrange point number 1 and number 2, and I'll show you diagrams of those in a moment. But they require about 13.3 kilometers per second from Earth, and they're only about 2.5 kilometers per second from the lunar surface. They are the worst payload payoff compared to LEO and GEO. They are well past the Van Allen belts. On the other hand, the access to lunar surface water makes it a great gas station once you get set up. Now, I should point out, in space, we do everything: braking, accelerating, turning in delta V with our point and shoot rocket motors. And what do we mean by that? Well, imagine you're an astronaut, you're in a spacesuit, you're floating in space. As far as you know, you have no velocity. You suddenly decide you want to move. So you get out your handy dandy fire extinguisher and you point it some direction and you squeeze the trigger for a second and off you go in the opposite direction. That is delta V, a change in your velocity. It was 0, now it's some fraction of a kilometer per second. Okay, I'm going to talk a bit more of that in just a moment. Now, here is a diagram of the moon in the middle, Earth is off to the left, and I'm showing L1 and L2. They're each about 55,000 kilometers off the lunar surface. However, no satellite will occupy the exact L1 point or the exact L2 point. Essentially, what they end up doing is orbiting about those points in these giant Lissajous orbits that are about 65,000 kilometers in diameter. Now, what the advantage of that is that these orbits are fairly low maintenance. Whenever you put a satellite in orbit, you're constantly having to do orbit maintenance burns in order to maintain your position and not burn up in the atmosphere or crash into the surface of the moon or something like that. So, however, because of the energy situation around L1 and L2, you don't have to do that much. So the beauty of that is you could host fleets of space stations in L1 and L2, and they would have gobs of separation and be able to function quite nicely while taking tremendous advantage of the water on the south polar region of the moon. The L-Cross mission conducted by PI Tony Cullebrete, another friend of mine from NASA Ames, showed that the lunar poles have hundreds of millions of tons of water ice. Nuclear-powered electrolysis can convert that into LOX and LH2, providing a convenient supply of rocket fuel. Okay. There. Now, in book 3, which takes place around 2100, Space Corp is dominating the satellite business line in LEO and has a sizable fleet of space stations at Cisluna's EML-1 and EML-2 orbits. So next up for them is a trip to Mars with a PB-11 fusion drive. PB-11 stands for proton boron 11. There's a variety of elements that you can combine to get fusion out of. Ionized hydrogen and boron 11 happen to be 2 of them. Anyway, that's being used on the SIS Pascal Lee, shown in the picture here, the book cover. And that cheesy looking guy down in the lower left is my good friend Pascal Lee. That's him up at the Houghton Mars Project base camp on Devon Island in the high Arctic and back in 2010. He's a hell of a guy, in my opinion, is Mr. Mars. And so it was only fitting that I name this spaceship after him. So let's talk about it a little bit. Basically, as you can see, this spacecraft, it's a little different from the typical ones that you see coming out of NASA designs and whatnot. Its dominant feature is the long truss member that goes about 500 meters. There's a slip ring and at the midpoint here, and around that we have a habitat ring, 200 meters in diameter, that rotates at 3 RPM for a full G of gravity. These spherical tanks that you see here are full of liquid hydrogen, which is the propellant that you use when you're using a fusion thruster. You don't just make fusion and have all that heat go to waste. You've got to squirt something into it so that it can make thrust. So it is, in effect, a reaction engine. These black-looking things that you see on either side of the space station are not solar cells, but instead they are radiators. there's an awful lot of heat produced by the fusion thrusters and also the nuclear fission reactors that you need to keep the lights on. And so they have to be cooled somehow. And so that's where you get these vast arrays of Brayton cycle radiators that you use to keep everything cool. The ship has a crew of 200 humans, and it can get to Mars. It can do a 64-day round trip to Mars with a total delta V of 153 kilometers per second. Now, a normal trip to Mars would be 942 days, and I will explain why that is in just a moment. But that's because typically the rocket ships that we have do not produce that much delta V in order to get where they're going. So if you've got an excess of delta V, as we do with the fusion thruster, then you can do things like a 64-day round trip to Mars. Now you notice also that I've got fusion thrusters on the mounted both fore and aft. One of the things that's become very popular on television, let's see, The Expanse, is they are constantly talking about doing flip and burn maneuvers. Excuse me. Essentially, they get their gravity by accelerating constantly, and they can bring their gravity up to 2 or 3 Gs if they want to. But normally they do a comfortable 1 G, and then when it's time to slow down, they flip and accelerate again in the opposite direction, and they slow down at 1 G. Imagine, however, if you had a spacecraft that's shaped like the Pascal Leap. It's got this long, rather ungainly or spindly-looking truss going down the center. You've also got this hab ring that's rotating at 3 RPM. Imagine holding a bicycle tire using a screwdriver going through the axle, and you've spun it. And I'm sure you probably tried this when you were a kid, and you try to rotate the bicycle tire, and you discover that it's pretty darn hard to move. So essentially, if you try to do that, a flip and burn, as they say, with something like the Pascal E, you probably cause it to tear apart along the truss somewhere. It still can do a flip and burn, but that would involve de-spinning the hab ring and doing a very, very slow flip. It wouldn't be a flip, it'd be more just, it'd take probably several hours to do a complete spin. And then you'd accelerate your remaining engine in the opposite direction and pick up where you left off. This is not a really good way to do something as precision as, say, entering an orbit around another planet, where I want to be able to, apply the brakes, hit the accelerator, apply the brakes, hit the accelerator, that kind of thing. Kind of like when you pull up to a stop sign. Very few of us are good enough to just hit brake only. We find ourselves sometimes having to apply accelerator and that kind of thing. So it allows you a lot more flexibility. Additionally, there's a lot of debris out in space, not just around Earth, but everywhere. So if you suddenly detect something that is on a trajectory with your spacecraft, you may suddenly find the need to decelerate. Well, you don't have time to do a flip and burn. Instead, you want to just pour the coals to the forward thruster and slow down a bit, and then off you go. I should point out, let's see, PV11 fuel is not as powerful as what you could get with, say, deuterium helium-3. It produces an exhaust velocity of about 4.5% the speed of light, whereas deuterium-3 produces about 8.9% the speed of light. So it's about half as powerful as what you can get from deuterium helium-3. However, unlike deuterium helium-3, it is safe, it is plentiful, and aneutronic. The plentiful is the operative word there. You can find boron-11 everywhere you look, and of course, protons are nothing more than ionized hydrogen atoms. And hydrogen is probably the most prolific atom in the universe. Now, the other downside is that it has a Lawson criteria, which rates how hard fusion reactors are to start. And it's rated at 500, which means it's very hard to start. Much harder than a deuterium-helium reactor would be. So that said, delta V, Hohmann transfers, hyperbolic transfers. Let's pause for a moment and take a crash course in rocket science with a little bit of orbital mechanics. Those of you who have seat belts, you are advised to attach them now. Excuse me. Okay, I should start out by saying that rocket technology that is ideal for lifting large payloads from the Earth's surface is not ideal for interplanetary travel. Modern heavy lift rockets have a thrust-to-weight ratio of about 1.5. Now, these launch vehicles have very high mass, ruggedized airframes designed to maintain structural integrity through intense G-forces and atmospheric buffeting. They're good for lifting heavy loads into LEO. They're not so good for interplanetary trips. Over here on the left is the Space Launch System, which finally launched back in November. It is estimated to cost $2.2 billion per launch, and that was as of a NASA 2021 audit. It is capable of boosting 130,000 metric tons. I'm sorry, 130 metric tons into LEO, and possible 45 tons to the moon. Then over on the right, we've got the Falcon Heavy, and it's made 5 successful launches so far. It costs about 97 million, not billion, per reusable launch. It's good for about half the payload of the SLS. And it's a pretty established technology, being based on the Falcon rocket. Elon's Starship is probably the immediate future of space exploration. It's designed to deliver 150 tons into LEO. Its best feature is that it can actually be refueled in higher orbits or for destinations in the inner solar system. It's so far only the top has had a successful launch. Elon seems to think that we're going to have a first full-on orbital launch in March of this year. When it's fully functioning and fully reusable, it's supposed to cost between $2 and $10 million per launch. Even if that's twice as optimistic as it should be, that's a pretty cheap price, especially compared to the SLS. It can boost 150 tons to LEO, which is more than the SLS. It basically uses these Raptor engines throughout, 33 on the booster and 6 more on the Starship. They run a combination of methane and LOX, and it's good for an exhaust velocity of 3,750 meters per second. Another term I'm going to be throwing around is specific impulse, 380 seconds. Essentially, that's a measure of the gas mileage that you get from a particular rocket motor. Think of it as how long in seconds can 1 kilogram of fuel produce 1 kilogram of thrust. If you think of it that way, then it kind of makes sense that you get a specific impulse of something like 380 seconds. Okay, now this design right here has been around for a little while. It's never flown, never been built. It's a more realistic Mars transfer design by a fellow out of Georgia Tech named Stanley Borowski. It uses nuclear thermal rockets and liquid hydrogen as a propellant. So these tanks right here would all be liquid hydrogen, and then you've got these relatively small Pee-wee class nuclear thermal rockets in the back end. Its habitat area is somewhat small, about looks like it's about 20 meters in diameter, and it rotates. So essentially, you've got some minimal amount of gravity provided for the crew, while they're on the way to Mars, where they are expected to be able to get there in just a few weeks, as opposed to the 6 or 8 months that a normal rocket trip would require. Note the thrust to weight ratio, 0.07, which is minuscule. It makes up for that fact, however, by the fact that these rockets fire continuously throughout the trip. Okay, here's another fusion power design, also by Stanley Borowski. Excuse me. Okay, its thrust to weight is 0.001. I mean, it's minuscule. However, again, this fusion rocket in the back end here fires continuously. It's expected to be able to get to Saturn in under a year. Normally, a trip to Saturn with our conventional Hohmann transfers and whatnot is a 10-year endeavor. So less than a year, pretty good improvement. Now, here we have Konstantin Tsiolkovsky's famous rocket equation. He's a Russian guy from way back when, and he is what I call the party pooper of space travel. His equation is why it's so damned hard to get from point A to point B in space. His equation is also the reasons it is at all possible to get from point A to point B in space. It's a fairly simple equation. Go back to our astronaut who was sitting there in space, not moving anywhere, but he's got his fire extinguisher. That's his rocket motor. Okay, at that point, his velocity is 0. Let's say that he squeezes the trigger on the rocket motor and holds it very steady and it thrusts through his center of gravity, and he thrusts for a certain amount of time, and when he gets done, he has a new delta V, his delta V max. He keeps accelerating the entire time based on the exhaust velocity of the whatever effluent was coming out of the fire extinguisher. Now, when he started out, he and his spacesuit and his full fire extinguisher had a particular mass. That would be known as the wet mass. When he got done, he and his spacesuit and his empty fire extinguisher have a new mass called the dry mass. So in other words, I've got this ratio here, which we call the mass fraction or mass ratio of the wet mass over the dry mass. And then I've got this lawn term in the middle. Essentially, what the lawn term does is every time I squeeze the trigger on my fire extinguisher, I squirt some effluent out the nozzle. That makes me move a certain amount based on the mass that is pushing. But I've also reduced my mass just a little bit. Okay, the lawn term allows me to correct for that. So essentially, if I had, say, a mass ratio of 10, and I plugged in that number in my handy dandy calculator and then punched the lawn function, I would get 2.3. Okay, essentially that's what accounts for the fact that I'm slowly leaking out however much fuel I have. The exhaust velocity is what effect that fuel is going to have on my forward speed. So let's take something like a chemical rock. One other point here. If I take liquid oxygen and liquid hydrogen and burn them, I get the highest possible temperature from a chemical reaction, and hence the highest possible exhaust velocity, 4.4 kilometers per second, with an ISP of about 450 seconds. It's the most efficient. However, liquid hydrogen is a bear to work with, and so you find a lot of places they switch to methane or kerosene or something like that, but they continue to work with liquid oxygen. In any event, let's take that exhaust gas velocity of 4.4 kilometers a second, multiply that by the ln of 10, which is 2.3. That means that whatever my rocket ship was would be able to go from 0 up to a maximum velocity of 10.1 kilometers per second before it ran out of fuel. Okay, any questions on that? Okay, no questions, take boards. That was what they used to always say in math class in West Point. The instructor would walk in, say, any questions? No questions, take boards. Then you'd have to all run to your chalkboards and start reciting on the day's problem. Okay, there are two ways to increase delta V max. The first way is to increase the mass ratio, which in effect means simply add more fuel. Now, I did a little Excel spreadsheet study of that, and I held the exhaust gas velocity constant, and I increased the mass ratio a little bit at a time. And as you can see, I ended up with a nice curve. And the knee in the curve happens to be at a mass ratio of around 10. That's the sweet spot. So in other words, if I start at the low end of the mass ratio scale, I get good returns for my fuel investment. But for anything higher than 10, the payoff diminishes rapidly. Okay, let's look at the second way. I can increase the VE, which is to say I can come up with a more advanced rocket motor. So instead of using, say, liquid oxygen and methane, I use liquid oxygen and hydrogen. I get a higher VE. Let's hold the mass ratio constant this time at 10. We determined it was a sweet spot. Let's keep using it. And let's vary the exhaust gas velocity. And as you can see, I get a nice straight line curve here. The takeaway message here is that investing in rocket engine technology beyond chemical rockets in order to increase VE is worth every penny. This is something NASA tends not to do. Okay, some practical thoughts about delta V. In practice, let's see, if I had a delta V max of 100 kilometers a second, I could actually reach a velocity of 100 kilometers a second, but then I'm in trouble. You have the problem of how do I slow down? Rocket ships don't have brakes and space has no air friction. So ideally, what I have to do is I have to stop before I get to 100 kilometers a second, and I have to turn my rocket motor in the direction that I'm traveling and apply it again until I slow down, until I get back to zero. Now this has some profound impacts on your mission profile. So for a, ideally, I would set aside a certain amount that I can use for accelerating and decelerating for the outbound and the return legs of my mission. And then I want to also have a 30% margin added on for my delta V budget. 30% margin is something NASA is very fussy about. No margin, no money. Okay, so a typical round trip mission profile would be something like this. This would be like, say, for a manned mission, I want to go to the moon and back. I would budget 70% for accelerating and decelerating, 17.5% outbound, 17.5% decel, and then 17.5% return acceleration. And then before I get back to Earth, I've got to do a 17.5% return deceleration. And then I've got this margin left over, so in case I have to do any corrections or maneuvering or anything like that in the middle. A one-way mission might look like this, and that would be, say, for a typical robotic mission. Example would be the Cassini mission out to Saturn. So they could budget maybe 35% outbound and 35% decel to get where they're going, and then they've got 30% margin left over for maneuvering around Saturn until they run out of fuel, and then they, as their last final thing, they crash the Cassini spacecraft into the Saturn upper atmosphere so that it wouldn't contaminate any of the moons. A flyby mission, on the other hand, might look like this. Here, I only have to worry about my outbound acceleration. A good example of that would be New Horizons. It went by Pluto not long ago. It went zipping by that thing. It made no attempt to stop whatsoever, and that was the end of that. Except that they did save some fuel because they wanted to go and divert their mission a little bit here and there in order to visit various Kuiper Belt objects, one of which they've already visited. So here you can spend nominally 85% outbound acceleration. You don't have to worry about decelerating, and your margin you might allow that to drop down to, say, 15%. Okay, that said, now that we're all very good rocket scientists, excuse me a second here. Let's see, learn a little bit about orbital mechanics after I get out of this sweater. There. And essentially, we're going to use a trip to Mars as our standard mission. Now, the way NASA thinks about going to Mars right now is strictly with the orbital transfer to Mars, and that would be the Hohmann transfer. NASA's all about saving mass, because mass costs a lot of money to lift up into space, and then trying to do a burn to get all the way to where you're going. This just costs money, 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 and Congress hates that. And so they cause NASA to have to cut corners left and right. So how do you get to Mars on an economy class Hohmann transfer orbit? Essentially, it's all about timing. You start out with the Earth down here at the southern end of our little diagram, and Mars at the beginning is 44 degrees ahead of Earth. Now I should, point out that Earth travels about 30 kilometers per second around the sun, while Mars travels 24 kilometers per second around the sun. Earth is at 1 astronomical unit away from the sun, and Mars is at 1.5 astronomical units. So what we do is, just as Mars passes this 44-degree mark right here, we gun the engines about 3 kilometers per second. This causes us to begin tracing an ellipse. And the size of the ellipse is such that it will just nick the Mars orbit at the rendezvous point. Now, if we didn't do anything else, we would simply retrace the other side of our ellipse, and we would eventually get back to where we started, except Earth wouldn't be there. Eventually, I don't know, it might take 5 years or something, but you would reunite with Earth, but you'd in the meantime do a whole bunch of elliptical orbits. So instead, when we get to the rendezvous point, we gun the engine once more by 2.65 kilometers per second. Why do we do that? Because by the time we get to the Mars orbit, we've slowed to 21.5 kilometers per second. And of course, Mars is going 24. So we gun the engines 2.65, and basically that allows us to orbit match with Mars. Now, we're not quite done. Orbit matching with Mars would mean that eventually we would be overcome by Mars gravity and we'd crash into the surface. Ideally, what we want is to orbit around Mars. So we've got to gun the engines one more time, 3 kilometers per second, and that will put us in a nice circular orbit around Mars at about 500 kilometers altitude. Now, altogether, this Hohmann transfer to Mars is going to end up costing about 9 kilometers per second of delta V, 11.7 if you add in a margin, and it will require 235 days of travel time. Getting home is roughly the same, except that I have to wait for planetary alignment before I can light my rockets. That takes a whopping 516 days. Hopefully you brought a book. The return leg is a little faster, only 191 days, but altogether I'm looking at 942 days for a standard low budget Mars mission. Now, 940 days is an awful long time. It's an awful long time to not have anybody get sick or injured, to not run out of peanut butter sandwiches, to not run out of oxygen or water, to not get cooked in the Mars interplanetary radiation. I have a sneaking suspicion that 942 days is one of the reasons why NASA has put so little effort into trying to send humans to Mars. They keep talking a great game, but they aren't doing a hell of a lot about it. You got to understand, Hohmann transfers are cheap, but they take forever. Okay, so if I don't want to do a Hohmann, what could I do? We could try what's known as a hyperbolic transfer, or what I like to call a drive-by rendezvous. Now, the other mission had an elliptical transfer. Essentially, you're going to gun the engines, that you're going to trace an ellipse around, which just nicks the orbit that you want to meet. A hyperbolic transfer will not just nick the orbit, it'll pass right through it. This is a 93-day round trip to Mars with a 17-day stay at the surface. Essentially, I wait till Earth is about here and Mars is about here, and then I gun the engines. Let's see, my departure delta V is 25 kilometers per second. That's a lot more than the 3 kilometers per second with the Hohmann. And along the way, I've got to decelerate quite a bit by 29 kilometers per second. So already, as you can see, I'm pushing 60 kilometers per second of delta V. My outbound transfer time, however, is only 33 days. And now I can stay at Mars for just a short time, in this case, 17 days before I've got to take off again and catch up to Earth. In doing so, my outbound delta V is going to be 32 kilometers per second. As I get close to Earth, I've got to slow down, and so I've got to do my so-called flip and burn for 22 kilometers per second. And you know, the net of all that is something like 110 kilometers per second. Round trip time, again, 93 days is pretty good. The 110 kilometers per second, again, you have to add your margin, so that brings you up to 143 kilometers per second. This is well beyond what we could accomplish with a chemical rocket. So, that said, oops, here we are. Here's a Saturn round trip with a drive-by rendezvous. Normally, a Hohmann transfer to Saturn is 8 to 10 years. This is a 922-day round trip with a 92 days stay time at Saturn. It's pretty cool. Basically, you take advantage of the fact that Saturn out at 10 AU is traveling considerably slower than Earth is. And so basically you go shooting out there like so, you hook up with Saturn, stay for your 92 days, and then you start heading back to Earth. Note, Earth will orbit the sun 2.5 times during the course of the mission. It takes, surprisingly, not that much more delta V than the Mars mission did. And so basically 129 kilometers per second, your total mission burn would become 168 with the margin. But again, this is well beyond what we could accomplish with a chemical rocket. Typical chemical rockets. This is the big Saturn F1, Werner von Braun standing next to it. Its exhaust velocity was a bit under 3,000 meters per second. Its ISP was about 300 seconds. It basically ran on liquid oxygen and kerosene. Here we have a much more sophisticated chemical rocket. It runs on liquid hydrogen and liquid oxygen. That's the RS-25 engine that they use on the SLS. It was also perfected on the space shuttle. Its exhaust velocity is about 4,400 meters per second, and its ISP is around 450. That's about the max that you can get out of a chemical rocket. Okay, now let's consider nuclear thermal rockets. In principle, they work pretty much like nuclear reactors in power plants. They use enriched uranium, U-235. That's the good part, instead of the U-238 that is more dominant in nature. Commercial reactors use a enrichment grade of 3 to 4%. Anything over 20% requires special regulations, lots of bureaucratic inertia. Weapons grade is considered to be anything over 80%. Solid core nuclear thermal rockets from the 70s used 93% enriched uranium. Now, before you faint, consider the nuclear Navy, nuclear submarines use up to 96% enriched uranium. And the US Navy has never had a nuclear power plant accident. Okay, how do you apply this to a nuclear thermal rocket? Well, I have this huge big propellant tank full of hydrogen. I don't need any oxidizer, so I leave that home. In the meantime, I've got this massive pump right here, which is going to pump the liquid hydrogen into the nuclear rocket motor. Essentially, I've got control rods which expose fuel rods. I remove the control rods, and that causes the fuel rods to begin heating up to the tune of some 2,750 kelvins. When they, as they get to be that hot, then I start passing the liquid hydrogen through. It heats up explosively and spews out the nozzle at about 9 kilometers per second. And we got that's about twice as good as what I was able to get with a chemical rocket. Okay, so that said, we had a nuclear engine rocket vehicle application program called NERVA back in the 50s, 60s, 70s. Spent about $1.4 billion over 17 years. That was a lot of money back then. Today, you know, it's not so much, but you know, back then it was a hell of a lot of money. The program was canceled by Nixon to pay for Vietnam. We did lots of static test firings, no actual flight tests. This is a test firing going on at Jackass Flats, Nevada in 1962 to 1969. This is a photograph of an actual nuclear rocket with its nozzle skirt, the control rods. The hydrogen source would be, is not shown, but it would be passed through these two pipes right here. Some of it would be used to cool the nozzle, then it's passed back into the reactor core where it heats up and goes out and makes thrust. Since the shutdown of the NERVA program in 1973, nuclear thermal propulsion has been progressing in fits and starts with very limited funding. SLS has been sucking all the money out of the budget since 2011. However, in 2017, NASA let out an $18.8 million NTP reactor design contract to BWXT, Babcock and Wilcox, and I forget what the X stands for, out of Lynchburg, Virginia. It does not use bomb-grade 93% enriched uranium, but 19.75% low-enriched uranium. A very clever idea. Again, anything below 20% eliminates a lot of the regulatory inertia of working with bomb-grade, highly enriched uranium and opens the field to more commercial players. Are you listening, Elon? So this would be the basic rocket itself. It's the same as the other one, essentially. However, being a low enriched uranium instead of high enriched uranium, the question is, how much could it actually produce in the way of thrust? I don't know. They never did get around to actually building it. They keep making noises like they're going to, but we don't know. We'll have to wait and see. There are, these, by the way, are considered solid core reactors. We have solid core fuel rods, and they are mounted in a fixed fashion inside this rocket motor. However, there are also gas core nuclear thermal rockets. They are more complex and considerably more powerful than the standard solid core. This one is called a nuclear light bulb. It works like an incandescent light bulb in a closed chamber. So I've got, imagine if you will, a very hot incandescent light bulb with a quartz glass element surrounding the typical tungsten filament. Okay, it's kept inside a container, and then I pass some kind of liquid hydrogen into the container. It heats up and it spews out the nozzle, making thrust. Okay, imagine the same thing, except that instead of my tungsten filament, I've got nuclear fuel in a gaseous form called uranium hexafluoride, and it stays inside this chamber right here. Basically, the nominal core temperature now is 8,300 kelvins compared to 2,700 kelvins for the solid core. My exhaust velocity has gone from 9 up to 30 kilometers a second, and my ISP is now up to 3,000 seconds. With this particular design, I could get something on the order of 48 kilometers per second delta V max. And as you can see, this 7 rockets mounted in a cluster here produced 37 million newtons. That's an awful lot of thrust. Okay, then we have, okay, this one was called a gas core closed cycle, meaning once I enter the uranium hexafluoride into this chamber, it never comes out. We also have the open cycle where I introduce the uranium hexafluoride into a chamber, and it reacts with the hydrogen, doesn't react, but it heats up the hydrogen, and together they spew out the nozzle producing thrust. It is able to produce nominal core temperatures of 55,000 kelvins. The exhaust velocity is now up to 98 kilometers per second, and the ISP is a good 10,000 seconds. Its delta V max would be on the order of 157 kilometers per second. That's really booking. The problem with it, it's uranium hexafluoride spewing out the back end there. It's highly radioactive, and it's basically going to contaminate your operating area for a very long time. In the case of gamma radiation, if I have a gamma ray photon, it speeds away at the speed of light, so it self-cleanses the area that it was contaminating. Uranium hexafluoride is a gas. It's only going to speed away as fast as, well, in this case, 98 kilometers per second. I suppose that's better than nothing, but it's probably going to linger around for quite a while. You certainly would not want to use something like this down close to the Earth's surface. It would strictly be something that you would relegate to using way out in deep space when you're far, far away from anything that you could possibly harm. Okay, so let's take a look at where we are. We're looking to do reasonable manned trips out to 10 astronomical units. That would be Saturn. We want to do maybe a 93-day round trip to Mars. And we've determined that we need 143 kilometers per second in order to do that. That'd be delta V max. For Saturn, we want a 922-day trip, and we want a delta V max of about 168 kilometers per second. Okay, what can we get out of a chemical rocket? 10 kilometers per second. Forget it. We're restricted to Hohmann transfers only. It's not a mission, it's a career. Drive-by transfers are out of the question. It's going to be multi-year mission durations, lots of money, high risk. Don't want to do it. Fission-based nuclear thermal rockets convert mass to energy at about 1%, which is pretty cool. Solid core can get me up to 21 kilometers per second. Gas core closed cycles, I can get theoretically 69 kilometers per second. Gas core open cycle, I can get 225 kilometers per second. That's pretty quick. So my conclusions, solid core, not going to get me to Mars or Saturn in any kind of a high-speed fashion. Gas core closed cycle, still not good enough for Mars or Saturn. Gas core open cycle, in other words, the dirty one, would be good enough for Mars and Saturn. But at the expense of making my immediate local area highly radioactive for a time. Okay, let's go back to looking at Stanley Borowski's fusion rocket. This is the Discovery 2. Now, the impetus for this rocket was they wanted to take the Discovery rocket from 2001, A Space Odyssey, and actually build a fusion-based rocket that was a practical version of that rocket. Hence, they came up with the Discovery 2. It's 240 meters long. It's about 60 meters wide. These are the radiators that are needed. You've got Brayton cycle radiators here for the fission rocket motor, but then you've also got reactor coolant radiators down in this area, which because you need something to keep the lights on as you're traveling along. Your propellant, the liquid hydrogen, goes in these propellant cryo tanks, And basically, they profess to be able to get you to Saturn in less than a year. Pretty good rocket ship design, a lot to like about it. Here's another view. He's got a 17-meter radius habitat section on 3 spokes. They're rotating at a little over 3 RPM, getting about 0.2 of a G. However, when your radius is that limited and you're only and you're rotating that fast, you're getting awfully close to Coriolis effects. We haven't really studied a lot about that because we haven't really put anything up in space and experimented with it. So we really don't know, but we think that something like this would definitely be a Coriolis problem. In other words, what you used to experience when you were on the merry-go-round as a kid and you were hanging on to the outer rim and your buddy was spinning the merry-go-round as fast as he could, and finally he ran off and had to go puke or something like that. That's the Coriolis effect. Okay.
Ejner, we are getting close to like 4 o'clock, and we do want to leave some time for questions. So can you finish up, kind of bring it to a conclusion?
I will do my best. Okay. Let's see. Okay, this basically what I wanted to show you right here is the reservoir temperature, the internal workings of the fusion motor. Essentially, it has an electron voltage of 252, which equates to almost 3 million kelvins. This, when you pass this hydrogen slush propellant into this area, it's going to get very, very hot, very, very fast, and it's going to pass out the exhaust at 347 kilometers per second. Okay, essentially, I'll leave this, I'll try to just get to the high points of this particular chart. But essentially, they only use a relatively small amount of deuterium helium-3 fuel mass, 11,000 kilograms, compared to an awful lot more liquid hydrogen. Okay, their idea was that they would go to Saturn and then refuel when they got there. And I'm saying, yeah, okay, that sounds good. Maybe I could triple up on the fuel mass and leave the propellant mass to be something I would do my replenishing of. The thing is, the other thing to consider is if I can get these kinds of performance figures from deuterium helium-3, I should be able to get about half that from PB11. PB11 being less performant. Okay, and the ideal part about PB11 is that you can find it everywhere, whereas helium-3 is pretty hard to find. Okay, book. For some reason, I called this book 5. That means it should be book 4. Anyway, this one is Enceladus. Enceladus, as you know, is a moon of Jupiter, and it's where we are expecting to find a good deal of a high probability of microbial life under the ice. Her crew of 3,300 will consist of genetically modified galacticans and humans who can withstand high doses of radiation and also have extended longevity. The craft is 15 kilometers long and it runs on deuterium helium-3 with a VE of 347 kilometers per second. My friend Dr. Jonathan Lenine is the namesake of this spacecraft. He's the astronomy chair at Cornell. Okay, this is another view of the rocket itself. And basically, again, the idea is that you don't go there and colonize. You bring your home with you, and that's what these 4 rings are. Essentially, those big rings that you saw on the cover of Cisluna, here's 4 of them. They just borrowed them. Okay. The thing to consider is how do we get helium-3 on Earth? Essentially, we get it in special nuclear reactors called, of which there's only one in existence right now, and that's in Spring City, Tennessee, the Watts Bar reactor. It bombards tritium. sorry about that. Lithium-6, let's see, tritium is produced by bombarding lithium-6 with neutrons in a nuclear reactor. The tritium then decays into your helium-3. Right now, China, Chile, Argentina, and Australia are the big producers of lithium-6. You've probably heard a lot of folks talk about mining lunar dust to get helium-3. Yes, there is a lot of helium-3 up there. Mining it, probably not such a hot idea. It typically is around 1.4 to 15 parts per billion. And that means that you'd have to process 150 million tons of regolith to get a single ton of helium-3. So Space Corps solves the problem by constructing a Watts-Bar style reactor in EML2 and bringing lithium-6 up from Earth. Okay, this is the real book 5, Pluto. That's Alan Stern, who is the PI of the New Horizons mission. Essentially, they're going to take this spacecraft and they're going to head out to Pluto and once again look for life. Pluto is speculated to have undersea oceans, and if it's got a heat source, there's a good chance that life will have formed. Another view of the Alan Stern, and it, however, uses it does not use fusion reaction. Instead, it uses positron catalyzed deuterium to make its propulsion. Now, one of the big rages in science fiction is to use antimatter to make your propulsion system. Now, you can get antiprotons, and typically this is what they're figuring to use. The problem with antiprotons is that they're extremely difficult to make, store, and manipulate. One mistake, and basically, you know, if you're using mass that's suitable for rocketry and you take out Iowa. Hence, antiproton rocketry is probably 500 plus years away. Unlike antiprotons, positrons, that is anti-electrons, are easy to obtain and store. If you've ever had a PET scan, I get them every couple of years, you have been subjected to positrons. There are a lot of common isotopes that emit positrons, notably krypton-79. It's a natural emitter with a half-life of 35 hours. It decays to krypton-78 with a half-life of about 9.2 to 10 to the forever. Anyway, the positrons emitted from krypton-79 can be used to catalyze deuterium fusion. This is a big deal. Why? Well, Positron Dynamics up the road from me in Livermore, Ryan Weed is the CEO there. He is positing that we should build a interstellar probe, one that would be able to go out to Alpha Centauri. And essentially, this would be a system block diagram of his device. Okay, it's about 6 meters long, and it weighs about 1.5 metric tons. It carries a lot of deuterium fuel, and a small amount of krypton-79, which it passes through a moderator, which then goes into a grid of deuterium, which makes fusion, which makes heat, and that's then spews out the nozzle of the rocket. The beauty of it, however, is that you've got all this krypton-79 that you then need to replenish, which you can do with a magnetic nozzle and a krypton blanket. So you've got krypton-78, and you're getting all this neutron bombardment down in this area, and you pass the newly formed krypton-79 back up into here, and you're back in business. It's brilliant. Here's the thing. Note the delta V, 24,000 kilometers per second. That's the total delta V, how fast this thing could go if you just lit that candle and let it run. With a mass fraction of 3.375, the VE works out to 19,000 kilometers per second. The best we could get from our fusion rocket was 347. Okay, that's why this is a big deal.
All right,
So,
let's see what we
it.
have here. So We have a question from Susan. Given the body mass losses, how would astronauts survive?
The body mass losses. Can you give me a little more context there?
I believe this is in regards to bone density, those types of changes in the human body.
Okay, this is why they typically bring astronauts back after 6 months after spending that much time on the ISS. We did have one fellow who spent a little over a year on the ISS. That was that twin study. And the idea was to find out just exactly what would be the effect of that. And as it turns out, he's still having all kinds of problems with bone density losses, and the radiation did not exactly do his eyesight any good. What that means is that you can go to space, but the way we do it right now, you can go to space, you can spend a time, but you cannot live there. And this is a big problem.
Okay, you've talked about humans making genetic alterations to survive in space. How much change will there be? Will we still really be one species?
No, we would not. We would be a new species, Galacticans. Essentially, what I'm envisioning is, first off, as I said before, the ability to withstand radiation is based on your ability to make radiation repairs. All DNA suffers the same amount to exposure from radiation. Okay, what differentiates various organisms is their ability to make repairs. Humans can make repairs. They're just not nearly as good as certain microbes like Deinococcus radiatolerans and certain others who can tolerate, say, 500,000 to 1 million rems of radiation with no loss of viability. Okay, we can examine these microbes and figure out what is their DNA structure that allows them to have this rapid repair rate, and we can introduce that, thanks to CRISPR, into the human DNA, and suddenly we have a radiation-hardened human. The other issue had to do with longevity. If you're going to go on a generation Starship ride, which I'm showing right here with the trip to Ross 128B, that's going to be something on the order of, it could be 100 years, 150 years. There's a ethical problem that arises if we put a whole bunch of people on one of these ships with the expectation that they are going to die off before they get to their destination, but in the meantime we'll have produced a replacement generation. The replacement generation is going to logically ask the question, hey, I didn't ask to go on this ride, why the hell am I here? And so my solution to this is to extend the longevity of my Galacticans. How do you do that? Greenland shark. The Greenland shark lives about 500 some odd years, possibly longer, we don't really know. However, we can examine the genetic structure of Greenland sharks, and one of the things that we're determining is that they have a way of reproducing the telomeres in their chromosomes so that their cells don't die off. But when we have tried this with laboratory rats, typically what happens is that the rats become very cancer prone. The interesting thing is sharks don't get cancer. So we just need to do a little bit more exploration and figure out, okay, what part of that Greenland shark's genome do we need to borrow so that we have a long-lived human who also does not get cancer. And essentially you get a crew that can expect to make it all the way out to Ross 128B, 11 light years away, 150-year trip, no problem. But at the same time, this also greatly reduces the logistical burden on this ship. You don't have to have a nursery.
All right. Many sci-fi novels propose that we will have people living in the asteroid belt mining for minerals. In most cases, there is friction and war between grounders and belters. Do you think we will be able to progress in a way that will not cause friction?
Yeah. basically, I think that okay, as you can see, I've got a fleet of 4 starships that I'm showing right here. They're not significantly larger than the Alan Stern, or for that matter, the Jonathan Lenine. They have a large habitat cylinder, very similar to an O'Neill cylinder that you may have heard of, mounted in on the inside there. It's about it's a kilometer in diameter, and ideally they'd be around 2, maybe 3 kilometers in length. You put 1,000 people in there. Okay, if you want to, essentially, this habitat can basically go anywhere it needs to. It can replenish its stores with what's known as ISRU, in situ resource utilization. And ideally, it can park at, say, a lucrative batch of asteroids and make a whole brand new version of itself to include a new crew. So this is how you would continue the diaspora. But essentially, by each ship not being dependent on Earth, you're going to remove an awful lot of the raw material that causes divisiveness and that sort of thing. Another thing, belters, they're like 7, 8 feet tall because they live in such low gravity. They're very weak compared to Earthlings because, again, they have such low gravity. A lot of them would have an extremely difficult time walking around on Earth. They'd break bones. Even the Martians had a similar problem. The people who live on the starships and interplanetary spaceships that I'm describing, there's no reason they can't go back to Earth if they want to. Okay, they're essentially the same size and bone density and everything as a normal human being.
Okay. You've been talking about our expansion into space. Considering the mess that we've made on this planet, should we expand to destroy others?
We should not. And the way we are not going to do that is we're going to bring our homes with us. We can go to another planet. Okay, we can examine it for microbes. We can harvest the DNA from those microbes. But for the most part, once I've got one sample of DNA, I don't need another one. I can replicate that as much as I want. And so basically, I'm not going to disturb that planet appreciatively. I will go out to the asteroid belt and I will harvest various stores that I need to replenish my own resources. But for the most part, I'm not going to be bothering that planet all that much.
Okay, very, very good. And then Kathy Moon offers this. If you never land, you don't need artificial gravity to provide extra bone mass. Comments?
If I never land, I don't.
If you never land, you don't need artificial gravity to provide extra bone mass.
Oh, but I might want to land. Okay, like for instance, I show trips, ships going on trips out to Saturn, possibly to Neptune, but coming back, and the people that are on board are maybe going to want to have shore leave, so to speak. They're going to want to go to Earth to travel around, to do whatever. I don't want them to be forbidden from doing so simply because they don't have the skeletal structure to support such a visit anymore. Humans were designed in 1G. We should not mess with that. It works.
So I'd like to take this opportunity to, first of all, thank everyone for joining us this afternoon for this very interesting talk that we've had with Mr. Ejner Fulsang. This was very, very interesting. And, thank you so much for coming to talk with us today.
Thank you for inviting me. You have no idea what a turn on is. It is to get a chance to talk about my favorite subject in front of a crowd like you guys.